All right. So down here we've got we were just about to finish this on Thursday, I think, and then the bell rang. So let's finish at least our thoughts on this page. I actually have more examples than this, but I think this will give us a good flavor for what we're trying to do here when we're trying to prove something is odd or even or neither. By the way, as we come to these, maybe if you have an intuition, start with that. I mean, I don't know. What do you think on this one? And then plug in and actually try here. And we'll do the same thing on that one. Do you have a hunch as to what it is? I don't know. This one we're almost done here. What do you think this one's going to be here? Remember, just to be clear, what I mean is, like, if we plug in negative z, do we get something in the end that's just the original function itself, g of z? If so, then it's even. If we get something that's exactly the opposite, that is the original function with a negative applied to the whole thing, then that's odd. And if neither of those things happen, then we've established that it's neither. Okay, so that's, you think that's what's going to happen? Let's see here. So what happens to this guy here? What's this term simplified to? That's a nice even exponent, so is that okay there? And then plus z. So this is what happens when we plug in plug in negative z. We get this. So I ask, is that the original function? Not quite. It's not quite equal to the original function, right? Is it the opposite of the original function? Like if you negated the entire thing. It actually isn't either of those things. Right? So therefore, it's neither. And in order to prove something's neither, you really do have to prove that it's neither odd or even. So we've done that. What about the next one? Do you have any hunch before we even start? Do you have any intuition? We got like some you're starting to realize that this might have to do with even and odd exponents, but like what about the natural log? And what about the division? What if we have both even and odd exponents? So we'll work on simplifying this. Do you have a hunch though? No, you're just checking. Okay. Even, odd, I don't know. Neither, it could be neither. That's also an option. So I'm going to do like you're doing right now too. Plug in negative x everywhere. And simplify. So up on top, this doesn't really matter. That's still just ln of x squared, isn't it? And down here, what is that? Negative 2x cubed plus x. Anyone want to throw in a bet now? Yeah, it seems like that. I mean, if we factor out the negative 1 on the bottom and throw it out front, that we get negative y of x, don't we? So that's the definition of what we mean by odd. Okay? And again, on any of these, this is what I want to see. But afterward, if you're like, really, it is, you can plug in a number and just to feel it out and see if is it really happening, the thing we said it would happen. Or graph it on your calculator in y1 and see, does it look like it has rotational symmetry, 180-degree rotational symmetry around the origin? You can see that that's true. I mean, case closed, we've already proved that it is true, but if you're not still, if you want a visual on it, you can. But good. Any other thoughts there? So I just wanted to like close out that discussion. We just didn't say quite as much as I would have liked to have said. This is the work I expect when I ask you to confirm algebraically or prove that it's even, or that's what we mean, is this. Not like, oh, it looks that way, or I tried with an example and it seems to work. No, I want you to prove it using this kind of approach. Okay. The next section I want to say a few words about. I honestly don't have a ton to say about the section. The book introduces to you 12 basic functions. So we'll go through and talk about a couple of them here. Most of them should be basic, that is ones you already know and love from Algebra 2 and prior experiences. And also ask you, just out of restraint, if you guys have not used the markers, see if you can do that. See if you can do it. I know it takes a lot of takes a lot of self-control, but I think you can do it. Oops. Let me clear the annotations on this. All right, so they declare these to be the 12 basic functions. I'll show them to you. You don't need to write them down necessarily. They're in the book. I really literally copied and pasted this from the book. And eventually I have a handout too that I'll give them to you on. But I also don't think you need to write them down because you know them too. Like this is y equals x. Like please, like you don't need to graph this in your note. Oh, is that y equals x? Okay. Oh. Okay. They're just like going through and identifying these so that I think we have like a launch pad for conversation about the stuff we were talking about on Thursday. Like we want to be able to ask like about all the properties we were talking about, continuity and boundedness and increasing, decreasing, mins and maxes, discontinuity, all those things in the context where we actually have something to talk about. So let's just get this on the page. I think that we all know these functions, yes. And by know, I mean you can like plot them from memory. You could even do some transformations with them probably. You can describe them very well using the properties we've talked about. These all should be very familiar to you, am I right? So far, so good. They're the first four. This one I'm going to just pause for a second and talk about because it's not very familiar to you probably. This last one is. So let's stop and talk about the greatest integer function for a second, and then I'll show you the next six too, the 12 basic functions. The greatest integer function works like this. Listen first, and then we'll look back at the graph. If I'm the greatest integer function, what I do is you give me a number, and then I give you back the greatest integer less than or equal to your number. We'll say that again. You give me a number, and I give you back the greatest integer less than or equal to your number. Okay, so if you give me, let's use an example here. You give me 2.7. I give you back, what's the greatest integer less than or equal to? 2.7. I give you back 2, exactly. So I'm looking for the greatest integer less than or equal to the number you give me. If I give you back 2.1, I give you back 2. In fact, I give you back 2 for a whole host of answers here. 2.5 also, and 2.6. I give you back 2. What if I give you 2? Also 2. What about 3? 3. The greatest integer less than or equal to 3 is 3. Okay. What about negative 2.7? What's the greatest integer less than or equal to?
3.
Yeah, negative 3 actually. So just make sure you're thinking carefully about this. You're always giving back the greatest integer less than or equal to the number that you're given. On your calculator has this function in it. It's under math num, like where you find absolute value, ABS. This is also there. Int of x is one way you can write it, and it's a great way to write it. It's commonly also seen in the literature in the following two ways. I forget whether I think your book uses this notation also. I'll write two different other ways that sometimes it's written. Sometimes people write it this way, and sometimes like with brackets, and sometimes people also write it this way with this kind of bracket. And actually that's my favorite way to write it, this way here, this last way. Just because it kind of captures what it does. It takes the number like down. In fact, if you're a computer person, then you might have heard of this function before. It's something called the floor function too. It takes the number like down to the floor, right? And there's actually another function different than this one called the ceiling function, and you can imagine what this symbol looks like, right? Yeah. So I like that. So another name for this function would be like the floor function. So after that discussion, is it clear why there are these constant pieces to the function? And why it's closed on the left and open on the right side of each of those segments? Okay, I just want to make sure that that picture reckons with what we talked about informally. Okay. And I think the reason that they're including that among these functions, I'm not sure that it's one of the basic functions, but it is a good one to just talk about, like constant intervals and discontinuities and all sorts of, we don't have any other graph of the ones we're looking at today that has like a jump discontinuity, and this one does, lots of them. So I think that's why maybe they're including it, is just so it's good for discussion. Absolute value function, you know and love. Exponential function and the log function, I think you know lots about. We're declaring e to the x and ln x to be kind of the basic function. certainly every other exponential function can be written in terms of this, e to the x, right? So I don't know if you remember how to do that, but and then the sine and cosine function they're putting up there as well. Don't get too scared about that. I think all of you should have some experience graphing sine and cosine for sure, no matter where what your last year experience was. But we won't, in this particular unit, we have like 3 units of trig coming here soon. So we'll like hit them hard, don't worry. We'll do lots of stuff with trig for sure. We'll go deeper than you've ever been before. But for now, at least, all I need to do is to have like a basic familiarity with the basic graph. Okay, we don't need to do any transformations yet of those. We don't need to ask you too much trig stuff yet. But I would like, they are good graphs for thinking about, again, some of the properties we're talking about. And then the last one I'll put up here is one that you've probably not seen before. So I think all the other ones, I just wanted to slow down on those two, the greatest integer function and this one, and just say something about it. I don't know that you'll really see it outside this unit again until calculus, but it is, again, it's useful because in the context of talking about properties of functions, this one has some interesting properties that none of the others do. Can you think about that? What those might be? And while you think about that, I'll rewrite the equation up here. Okay, so think about why, just from the picture even, what properties does this exhibit that are kind of unique among the other 12 functions? Here it is, 1 over 1 plus e to the negative x. And it's hard to read. It's under the bubble there. I apologize. So is there anything interesting about it that's not true about other functions up here? Yeah. I think that's kind of the big one, is that this has 2 horizontal asymptotes. Isn't that cool? Right? So, and visually you can see that. Can you algebraically, now that I've written it clearly, can you verify that that's true just informally, at least algebraically? Forget about the picture. If you put in infinity, if you put in like 1,000,000 for x, do you get something very close to 1? Try it. And if you put in negative 1,000,000, do you get something very, very close to 0? Try it. Okay? I think you'll see that algebraically it works. Confirms the picture you're getting too. Yeah? Okay. So again, these are the 12 basic functions by your book's declaration. There's nothing like sacred about these 12 functions in the general mathematical community. But they do provide a good, like I said, launch pad for discussing the properties we discussed on Thursday. So we want to be able to ask you in the homework tonight, and actually homework 2 and 3 has some questions about, they'll say like, which of the 12 basic functions these are, bounded below, and you'll list the ones, or which ones have only increasing intervals, or which ones have whatever. So the other thing I'd like to say something about today too, though, and I don't have anything more to say really about the 12 basic functions, right? At this point, we'll say some more tomorrow. But I'd like to say something more about piecewise functions, because it even seems, I heard like kind of murmurs about that in the warm-up today even too. You're like, oh, we could maybe come up with an equation for this. Notice all we had to do is come up with a graph. That was nice, wasn't it? But could you come up with the equation? Well, maybe you would, and maybe the technology you would use is piecewise defined function, right? Like maybe that you be like I'm not going to make you do this, but you go and try and figure out what the equation of your warm-up was. Yeah. Yeah, your calculator is just a machine, but it is already convinced that it's 1. It's not 1. It's very, 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 very close to 1. Your calculator only has 10 decimal places. So to 10 decimal places, it thinks it's 1. Yeah. Anyway. Okay, so go ahead. See if you can prove to yourself that you remember how to graph piecewise defined function. Okay. Help your neighbors out on your table, because there might be some cobwebs here, but I think it is an important idea. So do those 2, and we'll share our answers in a second. If these are boring, modify them and make them more interesting. Okay? If you conquered these, like the T's.
Oh my god.
Yeah, we'll talk about
Do I use a pencil? Wait, no, wait. Forgot. What? Are you talking to me or Allie? Just draw little beads. Orange. No, because I like absolutely. It's just a bead, right? Oh shoot, me too. Wait, friend. Are there any decisions like
All right, we have two solutions up here. All right, so question on the first one. Let's come back together, if you will, please. Ladies, gentlemen. So what's I heard some people already say it, so go ahead and say it. What is this first one? Yeah, in fact, actually, this doesn't just like look like the absolute value function for when you see sometimes when the absolute value is first discussed in one or something in the book, like this is not just like something that looks like it. This is actually often the definition given for the absolute value function, right? And it should like make sense with what you think of. Right now, your understanding of the absolute value function might be along these lines, right? For a positive number, I don't do anything. For a negative number, I take the opposite, right? Like that's kind of exactly what maybe how you think of the absolute value function. I don't know. This second one, you could maybe more simply just write this way, right? Right? After having discovered what this really looks like, maybe that was not needed, huh? We can just write it that way, yeah? But that I think is an accurate picture of this. For both of these, are there discontinuities anywhere? No, actually, for neither one. Just keep in mind that even though we kind of think about these as being piecewise defined, these are one function. The pieces can come together, and in that case, it's not discontinuous at all, is it? Neither of them is. Just to make things more interesting, though, let's change this function. Here, we'll call this G2 of x. What if it was this? Right? How would that look? I'm going to modify your picture here. How would that look? Well, and I have a reason for doing this too. I'm not just being weird, okay? Promise. How would that look? Do you agree? Okay, now okay, everyone, hold on here. I believe there's an asymptote at x equals 1. Do you agree? I believe the function is also defined at x equals 1. Agree? Okay, like, C warm up and, right, okay, so we're good? There is in fact an asymptote here. So I just wanted to like share that with you, right? That's completely possible. It's still a function, and yes, that's still an asymptote. Let's move on, okay? Is that cool? So maybe someone like told you that when you had like a more infantile mind that couldn't handle the truth, okay? But now I think you can handle it, okay? I mean, you're big boys and girls now. Let's skip this one for the sake of time. Let's do this one right here because I think it's interesting. Okay. By the way, as you're working on this, I don't have much more to say to you guys today. I think we're in a good place. If you want more practice on graphing piecewise functions and working with them, number 3 on this packet that I just handed out has some problems of that type for you. You should be able to do all the problems in this packet at some point. I'd like you to finish this before the end of the unit. I'll check it on the review day, okay? And I'll maybe go come through and assign certain problems at some point. The thing I'm checking tomorrow is homework 2 from the book, though, okay? So you don't need to like rush to do this. But if you're like bored in English class, you can work on it, okay? All right, do the M and B problem. Do the M and B problem. It's fine. M and B are constant. X is the variable. Throw the paper towels away and get out, please. Homework 2 from the book tonight, please. That wasn't clear. Homework 2 is what I'm checking on. Homework 2. Oh, yeah.